Okay, this will get started. Are there any questions at this point about homework? Any issues from last time? Okay, well, I guess we can continue with the material we were working on as we started getting into simulation methods. I will say I'll stop a little early to hand back the homework ones and the solutions to those at the end of class. But for now, we'll just continue with what we had started to introduce at the end of last class, and that is the topic of Markov models. As I had mentioned then, a Markov model is something we would commonly represent through a weighted graph. So we'd have some set of states, which we would represent as nodes of a graph, some set of transitions that we would represent as edges of the graph, and then typically a weight function for the graph that would correspond to transition probabilities. So we might have a P1 and 2, probability of transition from state 1 to state 2, state 2 to state 1. You can have self-transitions of P1, 1, and so forth. And as I mentioned, we would formally represent a Markov model through three elements. We would have a state set, which would be the nodes of the graph, or canonically called Q. So that would be some Q1 through Qn. We will have a starting probability density, which we'll commonly denote by a vector P, and that would consist of the values of all of the probabilities, probability that the state at step 0, which we'll refer to as Q of 0, is any given Q sub I, and that will denote as Pi. And then the collection of all of these would be vector little p. And we would have a transition matrix. And the transition matrix, which we'll refer to as capital P, encodes the probability of moving from any one state to any other state. So that is the probability Q of n plus 1 is equal to any given Qj, given that Q of n is some other Qi, and that particular probability we will refer to as Pij. And those are the basic components of a Markov model. So are there any questions about that? Okay, so with a Markov model, we will typically be using these as a simulation technique. So that's going to be one of the main uses. So a lot of kinds of discrete simulations will be one way or another represented as Markov models, where the sequence of steps through the states are the thing we're trying to simulate. And as I had mentioned previously, that sequence of steps we might take in a particular implementation of models is known as a Markov chain. In some cases, we'll be interested in the Markov chain itself. Very often, we'll be interested in a particular property of the Markov chain known as the stationary probabilities, or the stationary distribution, which refers to basically if you ran the chain infinitely long, how much time would you spend in any particular state? So what fraction of the time would any given state come up? So that will typically be what we'll be trying to do when we work with a Markov model. So any questions about what a Markov model is, or any formal statement before we get into some analysis on these? Okay. So I think it helps to understand some of the properties of a Markov model by starting with a very simple Markov model and then looking at what happens when we try simulating that model. So what I'm going to do is move to a simpler model that has just two states. We'll call those Q1 and Q2. And we'll have a general version of a two-state Markov model, which means that we'll assume there might be a probability transition P12 from state 1 to state 2, P21 from state 2 to state 1, and we'll also allow for the fact that there could be a transition P11, what's referred to as a self-transition for state 1, and P22. And for these to be proper probability densities, we would generally need to have the condition that P11 plus P12 is equal to 1. And we would also have to have that P21 plus P22 equals 1. So if you're in state 2 with probability 1, you must go to some neighbor of state 2 on the next step, and likewise for state 1. So this will be the model we'll start with, and I will assume that we've got an initial vector of probabilities P1, P2, and that would mean that in simulating this model, what we're going to do is initially pick a starting state with probability P1 of it being state 1, P2 of it being state 2, which would imply P1 plus P2 equals 1. And then on each subsequent step, we're going to take transitions using these transition probabilities. So for in state 1, with probability P12, the next state is 2, probability P11 is 1. So is that clear to everyone? Okay, so let's start to look at what happens when we start simulating this model. So if we look at the vector of probabilities initially, so what is the probability Q of 0 is Q1, and what is the probability Q of 0 is Q2, or again, Q of 0 is what we mean by the state of the model at step 0. So this would be the initial condition, and that is given by this vector we've already seen here. It's part of the definition of the Markov model, that this vector would consist of the probabilities P1 and P2. So that is the probability distribution when we first start the model. And then what we'll want to see is how that probability distribution evolves as we start changing the model, so as we start running the simulation across successive steps. So let's go to step 1 and ask what is the probability distribution for Q1. So what is the probability Q1 is, or Q of 1 is equal to Q1, and what is the probability Q of 1 is equal to Q2. Well, given the way we've defined a Markov model, we can figure this out based on looking at the transition probabilities and looking at the probabilities of the prior step. This is one of the key assumptions, often known as the Markov assumption, that the state in the next step of a Markov model depends only on where it is in the current step, or at least only on a finite amount of memory of prior steps. But in this case, we're assuming a first-order Markov model. So the state will depend only on where it is at the prior step and the transition probabilities. In particular, what we're going to assume is that the probability it's in state 1 at step 1 is going to be derived by looking at two different possibilities. Either it was in state 1 at step 0, and it took the self-transition to stay there, or it was in state 2 at step 0, and it took this P21 transition to move to state 1. One of those two things has to be true for it to be in state 1. And so we can say the probability of this happening is the probability it was in state 1 at step 1, which we had here, times the probability it stayed there, which is P11, plus the probability it was in state 2 at step 1, times the probability it moved from state 2 to state 1 in the transition between these steps. So the probability then that it's in state 1 at step 1 is P1, P11 plus P2, P21. So did everyone follow that? Okay, so then let's derive the probability it's in state 2 at step 1. And then you're going to tell me what that should be?
P2 times P22?
Yeah, so it would be P2 times P22. So it could have been in state 2 at step 2. and then stayed there.
Plus P1 times P12.
Yeah, plus P1 times P12. And that is going to give us the probability it's in state 2. So either it was previously in state 1 and we moved to state 2, or it was previously in state 2 and stayed there. Okay. So is that clear to everyone? Okay, well, let's take this one step further and ask, what is the probability? The second state, so step 2 is Q1, and the probability state at step 2 is equal to Q2. Well, to derive that, we basically do the same thing we just did. We would say either it was in state 1 at step 1, we have that probability here, P1, P11, plus P2, P21, and then stayed in step 1, the probability P11, or it was in state 2 at step 1 with probability P1, P12, plus P2, P22, and then it moved to state 1 with a probability P21. So this whole thing then would be the probability it's in state 1 at step 2. And we could similarly ask the probability it's in state 2 at step 2, and that will be the probability it was in state 1 at step 2, P1, P11, plus P2, P21, times the probability it moved from state 1 to state 2, P12, plus the probability it was in state 2, that's P1, P12, plus P2, P22, times the probability it stayed there, which is P22. So this then would be the probability it's in state 2 at step 2. So is everyone with me so far? Okay, so it should become apparent pretty quickly that you wouldn't want to keep manually doing this for many more steps. But even just going through 2 steps, it should be also apparent that there is a pattern to this, that we're basically doing the same operations over and over. In particular, there's a pattern that we can represent very nicely using some of our tools from linear algebra. So if we look at the vector of, let's say, the probability of the state at step n, so that's Q of n, is Q1, and the probability of the state at step n is Q2, then we can describe that in terms of the probability vector at state n minus 1. In particular, we can describe it in terms of a matrix multiplication as P11, P21, P12, P22 times the vector of probabilities at step n minus 1. Q of n minus 1 equals Q1 versus the probability Q of n minus 1 equals Q2. And that's basically just what I was saying as we were working through the early steps of this. So the probability you're in state Q1 at step n is the probability you were in state Q1 at step n minus 1 times the probability you stay there, plus the probability you're in state Q2 at step n minus 1 and then move from 2 to 1. So that row of the matrix multiplication will give us this probability, and the probability we're in state 2 at step n is the probability we're in state 1 at step n minus 1, and then move from 1 to 2, plus the probability you were in state 2 at step n minus 1, and then stay there. So in other words, this product of this, which is simply our transition matrix, gives us one step of update of the Markov model. So does that make sense to everyone? Okay, so once we observe that, then that's telling us something important here, which is that this probability of being in Q1 or Q2 at step n can be explained by a series of multiplications by p tracing back to the initial starting vector. In particular, it's p raised to the nth power times the initial starting vector. So that's going to be the probability distribution at step n, just p to the n times our little p vector. So everyone follow that? Okay, so that is really the key to understanding a lot of the analysis tools we'll be looking at the rest of today, to recognize that simulating a Markov model is basically matrix multiplication. It all comes down to linear algebra, and if you get that, then you should be able to follow how we'll be using linear algebra ideas to analyze these models and to derive some interesting properties about them. Right, so just to give an illustration of that, let me start with a slightly more complicated model at this point. So let's imagine that we are doing a model to simulate some genetic sequence. I'm going to give a very high-level model where we're going to assume that we've got some, let's say, intergenic sequence. We've got some exonic sequence, and we've got some intronic sequence. And we're going to assume that if you want to generate a simulation of a genome, what you would do is sample bases from the intergenic region, and you would have some self-transition probability. So this won't be a very realistic one, but let's say 0.9. So 90% of the time when you get an intergenic base, we'll say the next base is also intergenic. And 10% of the time, we'll assume you start a new gene. Once you've started a gene, you may go around with some probability 0.8 of continuing that exon in your gene, and you may at that point introduce with, let's say, probability 0.1 an intron. And once you're in an intron, maybe 90% of the time you keep adding intronic bases, but 10% of the time you go back and start a new exon, and that would leave us 10% here probability that you're in your final exon. At some point you shift back to the intergenic region. So this would be a high-level model for generating a genome that is a mixture of intergenic, exonic, and intronic sequence. And you can imagine if you were really doing this as a real genome simulator, you would have more complicated modules within this. So within this intergenic region, you might have a set of base probabilities and transitions among them, and so forth. But for now, we'll just assume we have a three-state model. And I'm going to refer to this as, let's call this state Q1, let's call this one Q2, and this one Q3. So is the model clear to everyone? Okay, so to do a Markov model simulation, we would also need to assume some starting vector. And let's just say our starting vector is 0.2, 0.3, 0.5. Then we can just walk through a bit and see how we would simulate this model. All right, so what is the distribution of states at time 0 in this model? Just abbreviate that by Q of 0. What would that be? Yeah, it's just our vector P. So that's going to be 0.2, 0.3, 0.5. So then how would we derive Q1?
Multiplied by our transition matrix.
Yeah, so we'll need to see what our transition matrix is, and we encode all of the pieces of this model I've described. From state 1, we've got a self-transition of 0.8 and probability 0.1 moving to either of the others. From Q2, we've got a self-transition probability of 0.9, and we are assuming we can only move to state 1. And from state 3, we've got a transition probability of 0.9, a self-transition, and can only move to state 1 from there. So this would be our transition probability matrix P. And so if we want to derive Q of 1, what we would need to do is multiply capital P by this little p, which will give us 0.8, 0.1, 0.1, 0.1, 0.9, 0, 0.1, 0, 0.9 times 0.2, 0.3, 0.5. And if we work out the math, then what we would get is our probability of being in state 1 would be 0.8 times 0.2 plus 0.1 times 0.3 plus 0.1 times 0.5, and that is going to come out to, let's see, 0.24. How would we derive our probability of being in state 2? So, we need to to multiply the second row of this, take the dot product of this row with this vector here. So 0.1 times 0.2 plus 0.3 times 0.9. That's going to give us 0.285. Is that right? No, it should be 29. And then the last one would be 0.1 times 0.2 plus 0 times 0.3. And so we could keep doing this. We could keep running the model for successive steps. And if we wanted to figure out what the assignment of intron, exon, and so forth should be for, let's say, 1,000 consecutive bases of sequence, we could do this matrix multiplication 1,000 times, and we could figure out what the distributions of states were in all of those. Often this is not something you really want to do for more than a few steps, though. So in some applications, you really are trying to get the whole Markov chain, and then pretty much this is what you need to do. Just keep multiplying one step after another. Usually, since you're simulating, your initial vector would effectively be 1, 0, 0, or 0, 1, 0, or 0, 0, 1. But basically, each successive step, you're doing a multiplication of that with at least one row of this to sample the next state. But often what we're interested in, as I mentioned before, is where this goes over the very long term. So what is the distribution of states in the long term of the model? And I'll just tell you that if we kept running this model, it would eventually go to a particular final state, so the stationary distribution I told you about. But if we're interested in something in between that, or we're interested in the rate at which it approaches that, then we might have to look at things like figuring out Q of n, so p to the n times p, where n could be a fairly large but not infinite number. So one trick you can often use if you're trying to do a simulation for a long but still finite time is to try to use the following transformation. To recognize that if n is a big number, then p to the n times little p is going to be equal to p to the n over 2 squared times little p. And that may not seem like it's much of an advantage, but that insight is basically the key to a way of making a much faster simulation of a relatively large number of steps. It's known as successive squaring. And the idea behind successive squaring is simply that once we've observed that you can make this transformation, you can pretty much do the same thing recursively. So if p to the n over 2 squared is p to the n, then p to the n over 4 to the fourth is p to the n, and so forth. And you can pretty much say for a very large p, split it in half, and then evaluate the matrix that you get for p to the n over 2 and square that, and then evaluate what this is by splitting that in half to get p to the n over 4, square that, square it again, and so forth. And there's just a little complication, which is that this doesn't work if n isn't an integer, but you can get around that with the following algorithm. So we can say that, let's call this p of n, which we're just defining to be p to the n, is given by the following. If n equals 0, well, what would p to the 0 be? Well, it's a matrix. It's almost. Well, it's the matrix equivalent of 1. So what would that be?
Identity matrix?
Yeah, an identity matrix. So that would be our base case. If n is odd, then we can't do the successive squaring trick on that round. So what we'll do is return p times p of n minus 1. And if n is even, then we can do the successive squaring, and we can return p of n over 2 squared. And this would basically give us a way of evaluating p of n, or p to the n, for fairly large n, much faster than doing n successive multiplications. So can anyone tell me about how many multiplications you would need for this? What would be the order of it? Yeah, it would be order log n. So effectively on each recursion, at most half the recursions will end up in the n odd case, so pretty much the runtime is dominated by the n over 2 squared case. You need log n rounds of cutting it in half before you get down to the base case. So it's an order log n algorithm. Is there any questions about that? All right, so this is a generalization of a formula I'll just mention. It'll become important later. That is kind of an identity about these Markov models known as the Chapman-Kolmogorov equations. It works on a similar principle to successive squaring. And what the Chapman-Kolmogorov equation says is there's a way of computing the value p sub ij of n plus n. I have to explain what this means. So p sub ij, where we're parameterizing it by an integer here, means the probability of going from I to state j in exactly n plus n steps. And what the Chapman-Kolmogorov equations say is that this is the sum over any states k, so k equals 1 to the size of our state set q, of pik of n, pkj of n. So basically, the probability of going from I to j in n plus m steps is the probability of enumerating over all of the states we might have passed through at an intermediate step n, so all of those k, probability of going from there from I to k in n steps, and then going from k to j in the remaining m steps. And that works no matter how we split n plus m into two integers. It could be 1 and n plus n minus 1, or 2 and n plus n minus 2, however you split this. So that's just something to be aware of that will be relevant a bit later. Are there any questions about that? Okay, so this is telling us more or less how we can work algorithmically with simulations of a Markov model for finite numbers of steps. But very often, as I've said, what we're interested in is really the limit of infinite behavior. So what is the limit of this probability vector as n goes to infinity? And to understand that, we need to know a bit more about the theory of these systems. So in particular, for the Markov model we were talking about a couple of minutes ago, so the intergenic intron-exon one, I'm just going to assert to you that for that particular model, if we run that model for a very long number of steps, what's going to happen is it will eventually converge on the vector 1/3, 1/3, 1/3. And we can verify that if it ever makes it to that vector, it's going to stay there by multiplying through by the transition matrix. So that was, again, 0.8, 0.1, 0.1, 0.1, 0.9, 0, 0.1, 0, 0.9. Multiply that by 1/3, 1/3, 1/3. And what you're going to get out is 1/3 times 0.8 plus 1/3 times 0.1 plus 1/3 times 0.1, which is 1/3. 1/3 times 0.1 plus 0.9, which is 1/3. And 1/3 times 0.1 plus 0.9, which is 1/3. So in other words, we can verify pretty easily that if you get to this vector, so equal probability of all three states, then every successive application of the matrix will keep you in that probability distribution. So that is equivalent to asserting that this is what I refer to as a stationary vector, the stationary probabilities of this model, which we will commonly denote by a vector pi. And this in particular is asserting that for this transition matrix P, P times pi equals pi. Now it happens that it doesn't even matter what the starting vector is. No matter what starting vector we give to this model, it will always end up in the limit of enough steps converging on this vector pi. And that is what makes pi, by definition, a stationary vector of the model. In terms of linear algebra, what is this asserting about pi with respect to p? Yeah, so this is equivalent to asserting that pi is an eigenvector of P. And what is its eigenvalue?
1.
Yeah, its eigenvalue is 1. So in this case, we end up with a model that is going to converge on a particular value of pi that is an eigenvector of P with eigenvalue 1. And recognizing that a stationary vector is an eigenvector with eigenvalue 1 is really the key to understanding how these models work and understanding some of the ways that a model may exhibit this typically desirable behavior of having a stationary vector, and also some of the ways that a model like this can fail to have a stationary vector. So one of the things that we can observe is that not every Markov model actually has a stationary vector pi. And it helps to understand a bit about why it is that some models don't have that. So I'm going to draw another model here. Let's say we've got a state Q1, it's got a self-transition of 0.8, we've got a state Q2 has a self-transition, or a transition from Q1 of 0.1, Q3 that also has a transition of 0.1. But then I'm going to assume that each of these has a self-transition of 1. So say this is an alternative model. And this model, I'm going to assert, does not have a stationary vector, at least not a unique stationary vector. And we can observe that pretty easily by imagining if we had starting distribution 0, 0, 1, then that would mean that with probability 1, we start in state 3, and then no matter how long we run this model, we stay in state 3. So that would imply that effectively pi is 0, 0, 1. And if we started with p equals 0, 1, 0, then we would also get stuck in state 0, 1, 0. So this is a model that doesn't have a unique stationary vector. Unlike this model, with this one it matters where we start. Where we end up depends on where we start. And I've asserted to you, but not proven yet, that with this model it doesn't matter where we start. No matter where you start, you'll end up with the same stationary vector. In this case, the stationary vector you end up in depends on where you started. In some cases, you don't end up in any stationary vector for the majority of starting points. And we can see that with another model. So let's say we've got a Q1, Q2. And I'm just going to say there are no self-transitions. If you're in Q1 with probability 1, you move to Q2. If you're in Q2 with probability 1, you move to Q1. Then if we started with the initial probability vector 1, 0, then on the next step of the model, the probability vector is 0, 1. On the next step is 1, 0, and so on. And in general, if the starting vector were p, 1 minus p, then the next step it would be 1 minus pp. The next step it would be p, 1 minus p. So basically, this model is just flipping the probability distribution on each successive step. So there are models that have a defined stationary vector, and often that's what we're trying to figure out with these models. There are others that could have multiple stationary vectors. We usually wouldn't refer to them as stationary vectors in that case, but multiple vectors that can converge on, and there are models that don't converge on any given vector. So does that make sense to everyone? All right, so if we want to understand some of the theory behind Markov models, it helps to understand what it is about these models that prevent them from having stationary vectors. So if we start with this one, what, in a sense, is wrong with that model? How can we know just from looking at this that it's not going to have a unique thing it converges to?
It can't move out of states Q2 or Q3.
Yeah, so we know if you start in state Q2, there's no possible way to get to Q3, and if you start in Q3, there's no possible way to get to Q2, so we can't have a unique final state. So that relates to a property of Markov models known as ergodicity. So a Markov model is referred to as ergodic if for any qi and qj, there exists some path with non-zero probability from qi to qj. So we could say equivalently, there exists some n such that probability ij of n is strictly greater than 0. Some n greater than 0. And that would be true for any ij. So a Markov model that has this property is said to be ergodic. This is not an ergodic Markov model, so that one is going to fail this test, and that would explain why it doesn't have a unique stationary vector. And this one, though, is ergodic. So this one, from any state, you can get to any other state. If you're in state 1, the next step you'll be in state 2, and vice versa. So it's a little more complicated to understand what's going on there. But we can start to think about that a bit by going back to our interpretation of this as linear algebra and thinking about what it says to apply one of these models in terms of linear algebra. So in particular, we're assuming that we've got, let's say, some vector pi such that p times pi equals pi if there exists a particular, if there exists a stationary vector. But in the general case, if we have any vector p, or any matrix p, we can always think about that matrix in terms of the full set of eigenvalues. So pi, we would say, is eigenvalue, or eigenvector 1. So let's say there's some eigenvector 1, and that's going to have lambda 1 equals 1. But we can also imagine there's some x2, some x3, etc. Or in the general case, if this is an n-state model, we're going to have n eigenvectors. It's possible you have repeats and then things get more complicated. But let's say canonically we have n eigenvectors. Then what we can say is that if we take any particular starting vector, p, then that can be decomposed into a linear combination of these eigenvectors. So if we have an invertible matrix, then any vector can be expressed in its eigenspace. So we will have a linearly independent set of eigenvectors, and so we can say that for any starting vector p, it can be expressed as some constant c1 times x1 plus c2 times x2, etc., up through cn times xn. Now, if we are looking at a matrix like this one that has a unique stationary vector, then what we would be assuming is that this is telling us something about the eigenvalues of that. So we have one eigenvalue that's equal to 1. We can't have eigenvalues greater than 1, or this wouldn't be P wouldn't be a probability matrix. It would turn probability vectors into things that are not valid probability vectors. So we would assume that we have one eigenvalue with value 1, and we would assume that all of the others have absolute value less than 1. So let's suppose that is the case, and start asking what happens when we apply the matrix to some arbitrary probability vector p. Well, after one step, we would say p times p is equal to c1 p x1 plus c2 p x2, etc., up through cn p xn. And what it means for these to be eigenvectors is that that would be equal to c1 lambda 1 x1 plus c2 lambda 2 x2, etc., up through cn lambda n xn, where the lambdas are the eigenvalues associated with those eigenvectors. And in general, if we did this for n steps, we'd say p to the n times p would be equal to c1 lambda 1 to the n x1 plus c2 lambda 2 to the n x2, etc., up through c sub n. And I guess I probably shouldn't have called this n, let's call it k, lambda 1 to the k xn. So for any arbitrary integer k, p to the k times little p is c1 times the first eigenvalue to the k, x1 plus c2, second eigenvalue to the k, x2, and so forth. So let's think about what happens to that and limit as k goes to infinity. So what happens to this first term here? What is the limit as k goes to infinity of c1? Yeah, it's just c1 x1 because lambda 1 is 1. What would happen to the second term? What is the limit as k goes to infinity of c2 lambda 2 to the k x2? Yeah, it's going to be 0 because we're assuming this has absolute value less than 1, so the limit as k goes to infinity, that goes to 0, and the same applies for all of the subsequent terms. So basically, this is going to converge in the limit on just the stationary vector. And understanding why that works with our assumptions here kind of tells us how this can break down. So under what conditions would it be possible for this to converge to multiple different states? What would have to be true for it to matter what p was for the final outcome? Well, what assumptions did we make about the eigenvalues and eigenvectors here?
That x1 equals 1, so x2.
Yeah, well, we assumed that x1 has an eigenvalue, lambda 1 equals 1, and we assumed all of the others had eigenvalues with absolute value less than 1. And that's basically where things can break down. So we're always going to end up with one of these having an eigenvalue of 1, or well, I'm not sure that's always true, but typically we'll end up with one that has an eigenvalue that's 1. But if we have others that also have eigenvalues of 1, then that's where we're going to get into the situation we see here, where there are different possible ending states. And we can see where that works out by considering, let's say, the model we were just looking at here. Right, so let's say we have that model. We'll construct the probability matrix, 28, 0.1, 0.1, 0, 1, 0, 0, 0, 1. So that would be encoding the probabilities defined in this particular matrix. And I'm going to assert that one of the eigenvectors of this matrix is 0, 1, 0. So what's the eigenvalue corresponding to that? Well, if we do the multiplication, 0.800, 0.110, 0.101 times 010, then what we're going to get is the first dot product of the first row with this is 0, dot product of the second row with this is 1, dot product of the third row with this is 0. So what's the eigenvalue? Yeah, the eigenvalue lambda 1 is equal to 1. So p times x1 is equal to 1 times x1. And the same thing applies for a second eigenvector. So if we have x2, there's going to be an eigenvector 0, 0, 1. And that's also going to have an associated eigenvalue that's equal to 1. And again, we could verify p times 0, 0, 1 is equal to 1 times 0, 0, 1. So that basically is what goes wrong with this model here. So when we do a decomposition of our initial starting vector into a linear combination of the eigenvalues, a linear combination of the eigenvectors, depending on what our initial vector p is, we'll vary what c1 and c2 are, but what we get out after multiple applications of this will eventually converge on c1 x1 plus c2 x2 when we raise k to the high enough power here. And so what we're going to end up with is depending on what C1 and C2 were, so depending on how you decompose your initial vector P into C1 x1 to C2 x2, so that is into some contribution of 0, 0, 1, and some contribution of 0, or 0, 1, 0, 0, 0, 1. Depending on what these coefficients are, you'll end up getting different final answers as to what this does in the limit as k goes to infinity. Does that make sense to everyone? All right, so in this case, the particular model is a three-state model. So we have a 3 by 3 matrix. There's going to be a third eigenvalue and third eigenvector. And in this case, this one's not so easy to see. It will come out to about 0.817, negative 0.408, negative 0.408. And this one will have an eigenvalue, lambda 3, of 0.8. So when we simulate the model over a long number of steps, the contribution of this eigenvector is going to fade away, but whatever the contributions of these ones were is not going to fade away. So if our initial starting vector had been, let's say, P equals, I don't know, let's say it started with equal probability in each state, then what you would want to do is figure out how to explain 1/3, 1/3, 1/3 as a linear combination of these three different vectors here. That would derive some C1, C2, and C3, and then based on that, you would be guaranteed that in the limit of a large number of steps, whatever C1 and C2 you came up with, those would be the things that would tell you the final state distribution. And this, you can guarantee that's going to be C1 equals 0.5, C2 equals 0.5 for this vector. So does that make sense to everyone? All right, so it's a little more complicated to see what will go wrong in this case. So let's go through with that. So just to redraw that here, we've got Q1, we've got Q2. So what would the transition matrix P look like? So we would have P sub 1, 1 in the upper left. So what's that?
0.
0 and 1, 0. Yeah, that's 1 and that's 0. So that is our matrix. And then if we want to analyze this one, we would want to know what are the eigenvectors of this matrix. So I'll tell you that one of the eigenvectors, x1, is 1/2, 1/2. And we can verify that pretty easily. So what's the eigenvalue for that eigenvector? Yeah, so you do the multiplication, you get out 1/2, 1/2. So that tells you that P times x1 is equal to 1 times x1, so lambda 1 equals 1. Right, so the other one I will assert is the following. 1/2 minus 1/2. So what is the eigenvalue corresponding to that eigenvector? Yeah, so this one will come out to -1. So if we take the multiplication 0, 1, 1, 0, 1/2 minus 1/2, what we're going to get out is minus 1/2, 1/2. So in other words, P times x2 is equal to -1 times x2. So lambda 2 equals -1/2. And that's going to tell us that, in general, if we have some decomposition, P equals C1 times x1 plus C2 times x2. Then if we take p times p, that's going to be c1 lambda 1 x1 plus c2 lambda 2 x2, which is going to be c1 x1 minus c2 x2. And p squared times p will be c1 lambda squared x1 plus c2 lambda squared x2, which is going to be c1 x1 plus c2 x2. And effectively, we'll just keep bouncing back and forth between these states. We'll always have a coefficient c1 of the first term, but then we'll alternate the sign on the second term. And so we can see how that would look with an example. Let's suppose p were 1, 0. Then if we wanted to decompose that into a linear combination of the eigenvectors, what we're trying to do is figure out c1 and c2 such that c1 1 half 1 half plus c2 1 half minus 1 half is equal to 1, 0. We can think of this as solving a linear system. We're trying to find the two variables c1 and c2 that make these two equations true. c1 times 1 half plus c2 times 1 half equals 1. c1 times 1 half minus c2 times 1 half equals 0. So can anyone figure out what c1 and c2 should be to make those true? Yeah, so c1 is going to be 1, and c2 is also going to be 1. So in other words, what we're going to get is the following. Okay, so we've said that p, which equals 1, 0, is going to be 1 half 1 half plus 1 half minus 1 half. And that then would tell us that if we take one step of the model, p times p is going to be lambda 1, 1 half plus lambda 2, 1 half minus 1 half, which is equal to lambda 1 is 1, so 1 half. Lambda 2 is minus 1, so minus 1 minus 1 half. And if we add that through, that's going to come out to 0, 1. So if you start in state 1 with probability 1, on the next step you're in state 2 with probability 1. And we can say in the general case, p to the k times p will be equal to 1 half plus minus 1 to the k, 1 half. And then it should be pretty easy to see that for even k, this is going to get us back to 1, 0. For odd k, it's going to be 0, 1. So that basically is why this model doesn't converge to a stationary state. And really the key for it not converging is this, that we have an eigenvalue that has absolute value 1 that is not our unique stationary vector. Okay, does that make sense to everyone? Okay, so that more or less tells us the conditions we need to have a unique stationary distribution. So we have a unique stationary distribution if our transition matrix has exactly one eigenvector that has an eigenvalue with absolute value of 1, and if you have either multiple vectors with value 1, or you have some with value 1 and some with value minus 1, then you get into the condition that you don't have a unique stationary vector. So any questions at this point? Okay, so that gives us an understanding of why this can fail, but it's not necessarily going to be a practical way of figuring out for any particular model whether it's going to fail. In some cases, we would be looking at a simple enough model that we can actually do this analysis, do an eigen decomposition of the model, figure out what the eigenvalues and eigenvectors are, and get a test that way. But very often in practice, that's not really going to be an option. Typically with these kinds of Markov models, when we're using them for simulation, the model you're trying to simulate is going to be something much too big to actually do linear algebra with, often too big to explicitly represent in a computer at all. So we often need to use various kinds of proof techniques to figure out if we're working with a model that has nice properties, because it's just too complicated or too big to actually do all of the linear algebra. And it turns out there is a nice test you can use to figure out whether a Markov model will have that property of having a single eigenvector with eigenvalue 1. And the test is as follows. So we ask, does there exist any n greater than 0 and delta greater than 0? And it's important that this is a greater than, not a greater than or equal to, such that the minimum over all I and j of p ij of n, which again is the probability of going from state I to state j in exactly n steps, is equal to delta. So this is the test, and if that's true, then we know our Markov model has a unique stationary vector. So to see how to apply this, we can take those models we were looking at before. Well, let's start with this model. So this was the first one we looked at. In this model, we can say, let's pick n equals 2. And you might remember that none of the probabilities here were smaller than 0.1. So let's pick delta equals 0.1 squared over 2. So n equals 2, delta equals 0.1 squared over 2. That would be below 5. Then I'm going to assert that the test passes for that n and that delta. So in particular, if we are in, let's say, state Q1, Q2, Q3, if we're in state Q1, then there is some probability that in 2 steps we're still in state 1. That would have a probability at least as high as the probability of going around the self-transition twice, which is greater than delta. There's some probability we would go from Q1 to Q2 in exactly 2 steps. So you could do that by going Q1 to Q2 in the first step, then taking the self-transition. That would have probability greater than delta. We can go from Q1 to Q3 in 2 steps. So that could happen by taking the self-transition, then going to Q3. That would have probability greater than delta. And we could show that for all of the other combinations. So going 2 to 2, 2 to 1, 2 to 3, 3 to 2, 3 to 1, 3 to 3, they all work out. So that model passes the test, and we know it has a unique stationary vector. So did everyone follow that?
Is there a good way, is the delta just kind of arbitrarily chosen? Or?
Yeah, so you get to pick the delta for this. The important thing is just that you can come up with anything greater than 0. So basically pick the lowest transition probability and raise that to the nth power for whatever n you use, and that's a fine delta. Okay, so let's say we've got our second model. I'm not going to bother writing the probabilities because they're not really important except for these two. So can anyone explain why that fails the test?
Because you can't go back from Q3 to Q1 or Q2 to Q1 once you know those two.
Yeah, so no matter what n we pick, we can always say I equals 2, j equals 3, and then pij for any n is 0, so we can't pick a delta greater than or equal or greater than 0 for which this is true. Delta, this is always 0 for I equals 2, j equals 3, no matter what n we pick. So everyone follow that? All right, so the other model, it's a little more subtle what goes wrong here. Can anyone explain why that fails the test? And you can always get from state 1 to state 2 in some number of steps, and you can always get from 2 to 1 in some number of steps. So what goes wrong?
If you show something like n equals 2, you couldn't get from Q1 to Q2.
Yeah, so the way this is phrased, it's important that for a single value of n, it works for every pair I and j. So if we pick any odd n, then there's a non-zero probability of going from Q1 to Q2 or Q2 to Q1. But for odd n, the probability of going Q1, there's no probability of going from Q1 to Q2. That has probability going Q1. And Q1 to Q2 has probability 0 of happening in exactly n steps for any even n, so that one fails. So there's no particular n where every ij has pij of n greater than 0. Does that make sense to everyone? Okay, so that basically gives us a way of figuring out whether a model will converge on a unique stationary state. Now, figuring out the stationary state is another matter, and that can be quite a bit harder. So actually, quite often, the reason we're creating a Markov model is because we want to figure out the stationary state. So we'll see that in the next class, that a lot of the reason we use these is that we have techniques for designing a Markov model whose stationary state will be something that we're trying to figure out. So often the best way to figure it out is literally to just run the model and see what it converges to. But in some cases, we can use a somewhat stronger condition that I'll just mention here, and that we'll be using in subsequent lectures, known as detailed balance. This is also referred to as micro-reversibility. So detailed balance is a way of establishing some constraints on the possible values of pi. In particular, detailed balance is the condition that for any I and j, the stationary probability pi sub I of being in state I times the transition probability of going from I to j is equal to the probability of being in state j in the stationary state times probability of transitioning from j to I. So many interesting Markov models will have this property, and when you have that, then that at least gives you a way of establishing relative probabilities of different states. So basically showing that for any neighboring states I and j, we know the ratio of pi j to pi I. So this is often a property you want to look for when you're working with these models, because it just makes a lot of the analysis much easier. This also has a kind of simple test you can do that doesn't directly tell you what pi I and pi j are for any state, but at least tells you that your model will obey this property. And that's something known as the Kolmogorov criterion. And the Kolmogorov criterion simply says that if we take any cycle in the graph, so let's say some sequence of directed transitions that start in some state Q1, Q2, Q3, and so forth, up to some Qk, and then back to Q1. The Kolmogorov criterion says if for any cycle, the product of probabilities going one way around the cycle is equal to the product of probabilities going the other way, then we're guaranteed that our model has detailed balance. So in other words, if we were to take, let's say, this model here, I'll just put the probabilities here, then this would be the assertion that for any cycle around these states, if the probability of multiplying the edges, let's say going Q2 to Q1 to Q3, well, that wouldn't be a proper cycle. Let's say Q2 back to Q1, we have 0.1 times 0.1. That would be kind of a trivial one in this case. But basically, we had a more complicated kind of model, and we'll see examples of those next time. If you can verify that any cycle around the graph obeys this criterion, then you know that you have a model that exhibits detailed balance. Any questions about that? All right, so one last topic I wanted to introduce today, which will become important in a lot of uses of these models, is the concept of the mixing time of a model. So the mixing time essentially is how long you have to run the model before it gets close to the stationary distribution. And we'll in a moment be a bit more rigorous about what we mean by close to the stationary distribution. But essentially, this is something we can also understand with our linear algebra interpretations. So in particular, if we have our model and we've got our set of eigenvectors of the model, and we've got their associated eigenvalues, and let's say this is a model that converges on a defined stationary distribution. So we're assuming that x1 is pi, and that tells us that lambda 1 is 1. Then it must be the case that each of these others has absolute value less than 1. And that pretty much gives us the key for understanding how quickly the model will converge on this stationary state. In particular, if we have our eigendecomposition, then after one step, we're pretty much decreasing the contribution of each of the eigenvectors other than the stationary vector by a factor of at least the ratio of lambda 2 over lambda 1. And since lambda 1 is 1, that basically is lambda 2. So if we apply the model twice, we're decreasing the contribution of the other things by lambda 2 squared. And if we apply it, let's say k times, then we're decreasing it by a factor of lambda 2 to the k. So lambda 2 more or less is the bound on how quickly the transients die away and you converge on this value lambda 1. So if we are trying to define the mixing time to be the number of steps we need so that the transients die away by a factor of r, then what we would want to do is say that the mixing time would be defined by lambda 2 to the k is approximately r. And that tells us that k log lambda 2 is equal to log r, or in general that k is about log r over log lambda 2. So this is one way of thinking about what we mean by the mixing time of a model, that basically the ratio of those eigenvalues is giving you a way of understanding how quickly the model converges. Now, for algorithmic purposes, we often need a somewhat more complicated and more rigorous definition, because just as we worry about orders of runtime when we're talking about, let's say, a deterministic algorithm to solve a particular computational problem, when we're using Markov models to estimate a probability vector, we're often very concerned about this question of mixing time in an algorithmic sense. So how long do you have to run the model? And we'll be concerned with creating what are called rapidly mixing Markov models, which basically means Markov models that mix in a small number of steps, typically as expressed in the size of the Markov model. And to do that, we need a somewhat more rigorous definition of what we mean by the mixing time of the model. So I'll just introduce now some terminology, and we'll see next week how we actually will show that Markov models exhibit this rapid mixing property. So if we want to define this more rigorously, we need to start with something known as a variation distance. And a variation distance is basically just a way of measuring how far a Markov model is from its stationary vector. And we'll denote that by the notation delta sub q of t, which we'll define in a couple of different ways. So this we'll define as the maximum over subsets of our state set q of the following quantity. Probability the state at step t is in the subset given that our state at step 0 was some initial state q minus the sum over states qi in the subset of the stationary vector, or the stationary value pi I. So in other words, this is just saying maximizing over all subsets of the state set how different is the probability of being in that subset at state t from the probability of being in that subset in the limit as t goes to infinity? Does this definition make sense to everyone? It will often be easier to use an alternative variant or way of expressing this. So 1/2 q sub I, sum over q sub I in q. So 1/2 the sum over all the states of simply the probability q of t equals qi, given q of 0 equals some initial state q minus I sub I. So just the sum of the absolute values of the differences between the probability of being in state I at step t and the probability of being in state I in the limit as the number of steps goes to infinity. Or this would be equivalent to what we refer to as the difference between the L1 norm of the vector pi sub I, or the vector pi, versus the vector pi of t. So that makes sense to everyone? Okay, so there are some situations where we'll want to use an alternative measure that's maybe a little more intuitive. So we would define that as the maximum over states I of the probability q of t equals qi minus pi I over pi I. Just another way of thinking about what we mean by the distance between the current vector and the vector in the limit as time goes to infinity. But basically it doesn't really matter too much which definition we pick. However we define this, we can then use that to come up with a more rigorous and more algorithmically useful definition of the mixing time of the Markov model. And that we will define as follows. So we will formally define the mixing time to be tau sub q of epsilon. So it's parameterized by state q and a distance epsilon, which we'll define to be the minimum over times t, such that delta sub q of t prime less than or equal to epsilon for all t prime greater than or equal to t. So in other words, what is the shortest t we need to get to such that we're guaranteed that the variation distance is smaller than epsilon at that time and all times going forward. And that's what we'll usually formally mean by the mixing time of the model. Any questions about that? Okay, so I don't think we'll have time to get into any genuinely new topics. I'll just give a preview that in the next class what we'll be doing is looking at some of the uses of these models as a way of sampling from hard probability distributions. And then the class after that, the class after that, I guess, is a special case, but the one after that is going to be where we'll look at how we can actually prove that models have small mixing time, or put bounds on the mixing time. So the special case, I guess I'll talk about on Tuesday. I do want to stop at this point so there's time to hand back your homework assignments. So are there any remaining questions about any of this where we hand back the homework?
Okay.